Sound therapy is not a substitute for medical advice, diagnosis, or treatment from a physician or healthcare professional. Sound healing can complement some medical treatments. Please check with your doctor or healthcare professional about using sound therapy to complement medical treatment. Do not discontinue or suspend medical treatment without the consent of your doctor or healthcare professional. This presentation will be describing vocal sympathetic resonance. We'll start off with an introduction to vocal sympathetic resonance, then to stagnation and flow. We'll describe what is sound, then what is sympathetic resonance. Then we'll give several sympathetic resonance examples. We'll describe the research being done into cell and vocal resonance, dealing with Parkinson, Sonocytology, and how cancer can actually be shattered using frequencies. Then we'll go into a brief overview and an example dealing with vocal sympathetic resonance and a type of system we're using. And then we'll end with a brief conclusion. For several years now, I've been researching various aspects of sound frequencies and the effect these frequencies may have on people, places, and things. One of the findings I've come across is dealing with the human voice, and it operating in some respects like the human digestive system. Much like the digestive system, our body keeps the nutrients it needs and gets rid of, or tries to get rid of, the excess. To do this, however, some type of flowing movement must take place to prevent stagnation. With that premise in mind, and given a person's vocal snapshot, or audio wave file, I'm able to calculate the resonant frequencies that an individual's voice is sympathetic to. When these sympathetic frequencies are played back to the subject, it helps in facilitating these flowing movements. If this flowing movement doesn't occur, or seldomly occurs, we get stagnation. In nature, we see what happens when something becomes stagnant or sedentary. Once this flowing movement returns, we get a revitalization of the system.
Sound is a wave that we perceive with our ears. It makes our favorite music and it keeps us out of danger, but it's so much more than that. Hey everybody, thanks for checking out Dnews today. I'm Trace. Now listen up. Sound is extremely powerful. It's made of invisible waves of energy passing through substances, ground, water, air, particle to particle. The human ear can perceive these waves as long as their frequency is between 20 Hz and 20,000 Hz. Anything above or below that we can't hear, but they're still there, because these waves contain energy. And with enough din, you can make these waves do some incredible things. Outside of medical technology like ultrasound, one of the most commonly known ways to make sound do something is by breaking a glass. This works only when the sound wave is at the exact same frequency as the object you're shooting at. If you gently flick a wine glass with your fingernail, you will hear its frequency. Match that tone and turn the volume up, way up to like 11. And that glass will probably break. Also within the range of hearing is sound levitation. This is way cooler than breaking stuff, if you ask me. Sound levitation has been around for years, but until recently, we couldn't do much with the stuff once it was levitated. It just sort of hung there in the air. Thanks to advances at a Swiss university called ETH Zurich, we can not only levitate stuff, but we can move it around, adjusting floating fluids. This works by using the energy in the sound waves. In this apparatus, the energy waves reflect back and forth so quickly they form what's called a standing wave, or a specific point point where the energy from the sound can hold an object in midair. Think of it like these silly executive desk toys. The ball in the middle, that's the standing wave. The thing that they just figured out is how to move the stuff once it's levitating. Now they can use this system to manipulate liquids, combining and separating them, all without touching them with human hands, which is immediately applicable to drug manufacturing. That's kind of cool. These energy waves can do a lot of other stuff too. The LRAD, or long-range acoustical device, is a weapon that shoots sound. It's like a sonic death ray, but without the death part. It can produce so much sound that you feel physical pain, like 160 decibels. That's loud. Think NASA rocket launch. But it won't kill you. It just really hurt, like a sonic hurt ray. If you combine some of those technologies, sound can produce really strange effects. In the 1950s, NASA and the US Navy built a device that produces ultra-low frequencies, or ultrasonic sound. If you pointed it at a person and set it to 19 hertz, people would have vision problems and get spots and stuff because 19 hertz is the resonant frequency of the human eyeball. Kind of like that wine glass example we talked about. If you turn the volume up, people actually would have trouble breathing because the low frequencies were impacting the lungs like energy waves, and if you shot it through the ground, your skeleton would vibrate, causing nausea and joint pain. So which of these sound inventions is your favorite? The levitating ones for drug manufacturing, ultrasound, or maybe one of the ones that are used for evil? Share your thoughts with us, and we'll see you next time on Dnews.
What is sympathetic resonance? It's a harmonic phenomenon wherein a formerly passive string or vibratory body responds to external vibrations to which it has a harmonic likeness. The classic example is demonstrated with two similar tuning forks, of which one is mounted on a wooden box. If the other one is struck and then placed on the box, then muted, the unstruck mounted fork will be heard. In similar fashion, strings will also respond to the external vibrations of a tuning fork when sufficient harmonic relations exist between the respective vibratory modes. A unison or octave will provoke the largest response as there is maximum likeness in vibratory motion.
Beautiful, light, and flexible, the Tacoma Narrows Bridge was built like no other suspension bridge. It was unique in its design and incredible in its appearance. But on November 7th, 1940, it all came crashing down. The collapse was one of the great tragedies in engineering history. Never had a suspension bridge so important met its end so catastrophically. But the Tacoma Narrows Bridge's true legacy was not in the frantic headlines generated by its collapse, but in the revolutionary changes it brought to the world of engineering and bridge architecture. That was Galloping Gertie's triumph. In the 1920s, America was prospering and optimistic. Skyscrapers and bridges were seen as symbols of elegance and power. Then, with the 1930s depression, cheaper and more efficient bridges were needed. As a result, bridges were made as simple as possible, graceful and slender works of art, beginning a trend towards light, flexible bridges. The Tacoma Narrows Bridge was proposed to connect the Olympic Peninsula and the Washington mainland. The Washington State Department of Transportation appointed Clark Eldridge to design the bridge. Eldridge's plan was examined by an out-of-state engineering consultant, the world-famous suspension bridge designer Leon Moseff. Moseff suggested replacing the 25-foot deep stiffening truss with an 8-foot shallow plate girder. Conforming to the trend, this lessened the cost of the bridge and gave it a slender, artistic appearance. In 1939, construction of the $6 million bridge began. On July 1, 1940, the Tacoma Narrows Bridge officially opened. It was the third longest suspension bridge in the world. Thousands of people attended the ceremonies. Thousands more worldwide were intrigued by the bridge's extraordinary width-to-length ratio and its exceptional flexibility. But the Tacoma Narrows Bridge had an even more fascinating characteristic: its bounce. Engineers were puzzled by these strange oscillations, but they did not doubt the bridge's safety. In fact, the bridge's movement attracted thousands of people who crossed the bridge just for the exhilarating experience of watching the car in front of them disappear. For this, the Tacoma Narrows Bridge was quickly nicknamed Galloping Gertie. Galloping Gertie proved to have many more benefits. It linked the less developed peninsula to the industrial Tacoma area. There was rapid land development and population increase. The bridge also benefited the military, connecting the McCord Airfield and Puget Sound Navy shipyard. All around, the bridge was a marvelous success, but Gertie began to run into problems. The engineers grew more worried about the bounce. Leon Moseff was contacted, but he assured them that it was not a problem. The engineers hired Professor F. Bert Farquharson at the University of Washington to build a scale model of the bridge and test it, while also studying the real bridge. We knew from the night of the day the bridge opened that something was wrong. On that night, the bridge began to gallop. Attempts were made to control the motion by installing hydraulic jacks and tie-down cables, but these proved ineffective. Farquharson observed a torsional twisting in the bridge model, different from the regular bounce. He recommended adding wind deflection devices, and preparations were made to install them. But the bridge did not meet nature's deadline. On the morning of Thursday, November 7, 1940, winds whistled across the Narrows. The bridge was rolling 2 to 5 feet. Suddenly, the bridge went into a lateral twisting motion. The sides rose and fell 28 feet up and down every 5 seconds, tilting at a 45-degree angle. Leonard Coatsworth was on the bridge when it began its violent twisting. He got out of his car and fled the bridge. His dog Tubby was left in the car. Farquharson arrived to record the event. The bridge had been closed by officials alarmed by the dangerous motion. Observers were worried, but very few expected what would come next. The first section of concrete from the center span broke off. The bridge began a violent motion. Steel girders twisted, cables snapped, lampposts broke off, and pieces of concrete fell. Then, 2 minutes later, a 600-foot portion of the center span plunged into the Narrows. Howard Clifford, a newspaper photographer, was one of the last people on the bridge.
It was bouncing so that it would go up where I was, and then it would snap down so fast, and I would go drop as fast as that went down. I would be going down. This was coming back up, and it hit me every time and knocked me down.
Along with pieces of the deck, Leonard Coatsworth's car and dog fell. The dog was the only casualty of the collapse. 11:10 a.m. saw the end of it all. Galloping Gertie hung limp and broken. The hopes it had inspired had been crushed. The tragedy was complete. Gertie's collapse came as a shock to the public. Many people were angered, blaming it on faulty engineering. They felt that their tax money had been wasted, and more would be squandered for conducting studies and rebuilding.
Nobody thought it would go down, no. I mean, if they thought it was going to go down, they would have closed it right away and tried to figure out what to do.
Several committees were appointed to analyze the cause of the collapse. The Federal Works Administration set up a group of professional engineers. In March of 1941, they announced their findings in a report. Part of the problem was that the solid plate girders on the side caught the wind like sails. The original truss design would have allowed the wind to pass through harmlessly. Also, due to its exceptional width-to-length ratio, the bridge was extremely flexible and fragile. Still, the winds had not been overly powerful. In fact, they scarcely exceeded 42 miles per hour. So what did prompt it? As the wind passed over and under the bridge, it created vortex shedding, where wind eddies formed on the opposite side. These eddies gave small pushes to the structure. Although the force wasn't especially great, the vortices caused the bridge to sway rhythmically. Eventually its motion became self-excited, meaning that it propelled itself. The bridge's drastic motion was caused by harmonic resonance. The basic idea is that everything vibrates at a natural frequency, which can be approached by outside forces. This concept is illustrated by a mathematical theory later suggested by Theodor von Karman. On that day, the frequency of the wind was close to the bridge's natural frequency. This resulted in a very small denominator, which made the amplitude of the motion huge. Unfortunately, such science and mathematics were overlooked at the bridge's construction. Galloping Gertie's collapse drew attention to them, and it continues to be a challenging puzzle for engineers all over the world to study and learn from. When Galloping Gertie collapsed, hopeful newspapers speculated that it might be rebuilt within the year. Then, World War II struck, and Gertie's remains were seen as a valuable mass of steel, and the state paid workers to salvage the material. Meanwhile, Farquharson had conducted groundbreaking studies on the model bridge, greatly advancing wind tunnel testing. British engineer W. Austin came to study the Second Narrows Bridge to help plan an English suspension bridge. Quote, "The whole of bridge engineering has profited by the fall of the Narrows Bridge. The subsequent research at the University of Washington is one of the most significant steps in bridge design in many, many years." Indeed, the Tacoma Narrows Bridge was followed by the Mackinac Strait Bridge and the Verrazano Narrows Bridge, both benefiting directly from the lessons it taught. Before launching plans for a second bridge, it was decided that the solution to offer least wind resistance was an open stiffening truss. No expense was spared in building the second Tacoma Narrows Bridge. The bridge had 33-foot stiffening trusses, wind grates, and hydraulic shock absorbers. It was the most technologically advanced bridge of the time, and the years of research in aerodynamics and mathematics triumphed in enriching the science of bridge engineering all over the world. A writer called the second Tacoma Narrows Bridge epoch-making. Galloping Gertie's sequel, fondly nicknamed Sturdy Gertie, set the standards for modern bridge design, terminating the trend of lighter, flimsier bridges. Wind tunnel testing is now mandatory for all suspension bridges. The second Tacoma Narrows Bridge picked up where its predecessor had left off. The tragedy of Galloping Gertie's collapse led to triumph, revolutionizing science and architecture, directing the change from light, flexible bridges to strong and dependable bridges, and bringing a wealth of new knowledge to the engineering world. And although an unprecedented initial success resulted in tragic failure, the Tacoma Narrows Bridge rose to triumph in the end. Stable, safe, and still beautiful, Sturdy Gertie remains as a lasting testament, power achieved by grace and artistry, and a triumph that has shaken itself out of the ashes of tragedy.
So, well, I do applied math, and this is a peculiar problem for anyone who does applied math, is that we are like management consultants. No one knows what the hell we do. So I'm going to give you some attempt today to try and explain to you what I do. So dancing is one of the most human of activities. We delight at ballet virtuosos and tap dancers, who you'll see later on. Now, ballet requires an extraordinary level of expertise and a high level of skill, and probably a level of initial suitability that may well have a genetic component to it. Now, sadly, neurological disorders such as Parkinson's disease gradually destroy this extraordinary ability, as it is doing to my friend Jan Stripling, who was a virtuoso ballet dancer in his time. So great progress in treatment has been made over the years. However, there are 6.3 million people worldwide who have the disease, and they have to live with incurable weakness, tremor, rigidity, and the other symptoms that go along with the disease. So what we need are objective tools to detect the disease before it's too late. We need to be able to measure progression objectively. And ultimately, the only way we're going to know when we actually have a cure is when we have an objective measure that can answer that for sure. But frustratingly, with Parkinson's disease and other movement disorders, there are no biomarkers. So there's no simple blood test that you can do. And the best that we have is like this 20-minute neurologist test. You have to go to the clinic to do it. It's very, very costly. And that means that outside of clinical trials, it's just never done. It's never done. But what if patients could do this test at home? Now, that would actually save on a difficult trip to the clinic. And what if patients could do that test themselves, right? No expensive staff time required. It takes about $300, by the way, in the neurologist clinic to do it. So what I want to propose to you as an unconventional way in which we can try to achieve this, because you see, in one sense at least, we are all virtuosos like my friend Jan Stripling. So here we have a video of the vibrating vocal folds. Now, this is healthy, and this is somebody making speech sounds, and we can think of ourselves as vocal ballet dancers, because we have to coordinate all of these vocal organs when we make sounds. And we all actually have the genes for it, FOXP2, for example. And like ballet, it takes an extraordinary level of training. I mean, just think how long it takes a child to learn to speak. And from the sound, we can actually track the vocal fold position as it vibrates. And just as the limbs are affected in Parkinson's, so too are the vocal organs. So in the bottom trace, you can see an example of irregular vocal fold tremor. We see all the same symptoms. We see vocal tremor, weakness, and rigidity. And speech actually becomes quieter and more breathy after a while, and that's one of the example symptoms of it. So these vocal effects can actually be quite subtle in some cases, but with any digital microphone and using precision voice analysis software in combination with the latest in machine learning, which is very advanced by now, we can now quantify exactly where somebody lies on the continuum between health and disease using voice signals alone. So these voice-based tests, how do they stack up against expert clinical tests? Well, they're both non-invasive. The neurologist test is non-invasive. They both use existing infrastructure. You don't have to design a whole new set of hospitals to do it. And they're both accurate. Okay, but in addition, voice-based tests are non-expert. That means they can be self-administered. They're high speed, take about 30 seconds at the most. They're ultra-low cost. And we all know what happens. When something becomes ultra-low cost, it becomes massively scalable. And so here are some amazing goals that I think we can deal with now. We can reduce logistical difficulties for patients. No need to go to the clinic for a routine checkup. We can do high-frequency monitoring to get objective data. We can perform low-cost mass recruitment for clinical trials, and we can make population-scale screening feasible for the first time. We have the opportunity to start to search for the early biomarkers of disease before it's too late. So, taking the first steps towards this, today we're launching the Parkinson's Voice Initiative. With Aculab and patients like me, we're aiming to record a very large number of voices worldwide to collect enough data to start to tackle these 4 goals. We have local numbers accessible to 750 million people on the planet. Anyone healthy or with Parkinson's can call in cheaply and leave recordings, a few cents each. And I'm really happy to announce that we've already hit 6% of our target just in 8 hours. Thank you.
So Max, by taking all these samples of, let's say, 10,000 people, you'll be able to tell who's healthy and who's not? What are you going to get out of those samples?
So what will happen is that during the call, you have to indicate whether or not you have the disease or not.
Right.
You see, some people may not do it, they may not get through it, but we'll get a very large sample of data that is collected from all different circumstances. And it's getting it in different circumstances that matter, because then we are looking at ironing out the confounding factors and looking for the actual markers of the disease. Yeah.
So you're 86% accurate right now?
It's much better than that. Actually, my student Thanasis, I have to plug in because he's done some fantastic work, and now he has proved that it works over a mobile telephone network as well, which enables this project, and we're getting 99% accuracy.
99. Well, that's an improvement. So, so what that means is people will be able to people will be able to call in from their mobile phones and do this test.
Yeah.
And people with Parkinson's could call in, record their voice, and then their doctor can check up on their progress, see where they're doing in this course of the disease.
Absolutely.
Thanks so much, Max Little, everybody.
Thanks, Tom.
In 2004, Gimzewksi intended to record the movement of cardiomyocytes, which are heart muscle cells that beat in culture. Atomic force microscopy had already been used for probing the surface of E. coli and imaging biomolecular reactions as they occur. The heart muscle cells were sent to him by Carlo Ventura, a Sardinian medical researcher he had met at a conference in 2001. Gimzewski's cells were scheduled to arrive from Sardinia on September 11, 2001. But in the heightened state of national security on 9/11, the cells were deemed a potential threat and were seized by customs. Frustrated and impatient to begin his work with the AFM, Gimzewski borrowed a yeast culture from colleagues who were in a nearby UCLA lab down the hall. And when he put them under the AFM, he was surprised to discover that yeast vibrate with a regular periodicity. Though both AFM and STM are examples of a broader category of microscopy that nanotechnologists call scanning probe microscopy, the techniques by which each microscope interfaces with a sample are quite different. Unlike STM, which operates in this tunneling mode that I described earlier, in AFM, probes come much closer to sample surfaces. And this is a technique that researchers call contact mode. Members of Gimzewski's lab compare AFM reading the topology of a microscopic surface to a blind person running his finger over a line of braille. Borrowing Thomas Kuhn's phrasing, Gimzewski called the shift from light microscopy to probe microscopy a major paradigm shift. Rather than using lenses and waves, they were recording by feeling. And just to explain the difference between scanning tunneling microscopy and atomic force microscopy, like I said, here the probe is coming much closer to the surface of the sample, and it's actually running in raster fashion over the sample. And what that means is it's deflected depending on the topography of the nanoscopic surface. As the tip is deflected, that mechanical motion is converted either by a laser or by what's called a piezoelectric crystal, and is converted into electrical current, which is then used to map the surface. So that's the difference between the two techniques. Most basically, the AFM is much, much closer to the sample surface. So as a tiny cantilever, and the tip is less than 10 nanometers wide, is displaced, this piezoelectric crystal converts the nanomechanical motion into voltage, which then creates this map of the surface. But the difference that Gimzewski made was instead of dragging the probe over the surface of the sample, he and his graduate student, whose name was Andrew Pelling, held the AFM probe stationary on the surface of the yeast cell, so that the oscillations of the cell wall could themselves be traced. And this is the technique that Gimzewski named Sonocytology, which he compares to using your finger to feel a pulse. Yeast cells are about 5 microns in length, and they have walls that are much more rigid than most mammalian cells, which makes it easier to rest a microscopic probe on their surfaces in order to detect cellular vibrations. So most eukaryotic cells are much softer than that. Gimzewski discovered that yeast cells vibrated rhythmically and that the periodicity of the vibration was within the range of human hearing. Using a freeware program he had downloaded from the internet, he converted the vibrations that he had recorded with the AFM into a sound file. And the resulting sound was something like this. That goes on for much longer. The entity doing the speaking in my story is Saccharomyces cerevisiae, commonly known as yeast. Yeast is a unicellular fungus with a cell cycle similar to that of humans. The first eukaryote to have its genome fully sequenced, and a standard model organism in biology research, yeast is an organism that lends itself to multisensory encounters. It has been imaged extensively with light and atomic force microscopy, and anyone who's seen the bottom of a pint glass or has walked past a bakery can speak to yeast's olfactory and gustatory allures. It's fitting, then, that this species is also the first to have its cellular noises amplified and recorded. Sonocytology is a technique that was developed by nanoscientist and UCLA professor James Gimzewksi 10 years ago. It uses an atomic force microscope to record the vibrational movements of cell walls and then amplifies these vibrations so that humans can hear them. Yeast cells vibrate approximately 1,000 times per second, and humans can hear any vibration that has a periodicity in the range of 20 to 20,000 vibrations per second, or hertz. So the vibration of yeast cells is well within the frequency range of human hearing. In musical terms, it's about a C sharp to D above middle C. But the amplitude of their vibrations is too low to be within normal hearing range. So the cell wall of yeast is displaced only about 3 nanometers each time it vibrates. But by amplifying the vibrations of these cells, UCLA scientists are essentially turning up the volume on cellular vibrations. And what I want to ask in this talk is, how are these raw cellular vibrations converted into cellular sounds that scientists can interpret as conveying meaningful information regarding the dynamism of cellular interiors? What are the conditions that enable scientists to describe cells as actors capable of, to use their terms, speaking or screaming? And how might listening to cellular sounds eventually change how scientists think about cells? Beginning to experiment with the noise yeast produced when amplified, Gimzewksi and Pelling recorded the vibrations yeast made at different temperatures and in different solutions. Adding sodium azide, a chemical that inhibits cellular metabolism, to the yeast caused a noise that sounded like radio static. That one also goes on for a long time. Gimzewksi believes this sound is an indexical representation of the Brownian motion of molecules, since sodium azide stops all ATP-driven nanomechanical activity. That is, it shuts down cellular metabolism. On the other hand, when they doused the yeast in alcohol, the pitch of the vibration increased. In an interview, Gimzewksi claimed that, and this is a quote, he said, "It screams. It doesn't like it. Of course, yeast produces alcohol, as in beer production, but if you put strong alcohol, like Absolute vodka on it, if you like, then it screams. It screams. It doesn't like it." He goes on to speculate that this screaming is the sound of molecular pumps working overtime to expel the alcohol from the cell. While the sounds produced by sonocytology are conversions of surface vibrations of yeast cells, researchers believe these sounds provide access to the workings of the cellular interior by signifying cellular metabolism and movement. So, describing the technique that he developed, Gimzewksi says, "We gently touch a cell, a living cell, and we listen. They actually produce a kind of music, and you can hear it." He says the music made by the cell is amazing and beautiful. Now, characterizing a vibrating cell wall as music is predicated upon a definition of sound as something audible not only to the ear alone, but to the ear with the aid of technical amplification. In the 1960s, American composer John Cage traveled just down the street to Harvard to listen to his circulatory and nervous systems in an anechoic chamber. And this experience led him to conclude that the entire lived world is sonorous and resonant. As he put it, that we have no ears to hear the music the spores shot off from basidia make obliges us to busy ourselves microphonically. Yeast are already making music. We just have to heed John Cage's advice and busy ourselves microphonically. Gimzewski also compares listening to the vibrations of yeast to eavesdropping. He describes the experience as akin to standing outside of a factory and hearing the hum and beat of machines operating inside the factory walls. He points out that during the Industrial Revolution, trained mechanics could diagnose what was wrong with a machine just by listening to it. Extending and concretizing that analogy between cells and machines, Gimzewski is currently applying sonocytology to clinical diagnostics by listening for the difference between healthy and cancerous cells. He believes that sonocytology has potential diagnostic applications because cancerous cells metabolize more quickly and therefore vibrate at a higher frequency. And I've listened to some of these recordings. I'm no expert, but most people can hear the difference between a healthy cell and a cancerous cell. His ultimate goal is for clinicians to be able to detect cancer at an early stage just by listening to the cells. Now, cellular sounds are not meaningful to the cells themselves, but they could be made meaningful through human audition. Nonetheless, some scientists have suggested that the vibrations picked up by the AFM are indeed signals that the cells themselves are using to communicate with one another. So that is, they believe that the cells are already talking to one another, and we're just listening in.
So it's a pleasure for me to be here to give you a kind of general talk on some work I do which has to do with cell vibration. And I'm in the chemistry department at UCLA and also in the California Nanosystems Institute. So this is something, when you think of chemistry, you perhaps think of atoms, solid, materialistic types of things. But in many ways, you can think of chemistry to be actually vibrations. And in quantum mechanics, Erwin Schrödinger, who actually is one of the people who described quantum mechanics in a very reasonable way, he actually used musical theories. Could I have the next one? So, in a sense, if you consider an atom is mainly actually nothing. There's nothing there. But it can be considered to be a type of wave-like, wave-like existence. And on the left, what you see are the fundamental modes of a normal string, like a guitar. And if you play guitar, you know how you can play harmonics. So these would be the fundamental, the first one. The second one is a harmonic. And de Broglie, who actually described the quantization of atom, he actually just used this type of theory here. But you imagine now that the string is a circle. That would be the electron in some orbit, and you can fit in a certain number of waves perfectly into a circle. And so therefore you have the different modes of vibration, if you like, of the electron in the atom, and that perfectly explains the quantum mechanics of atoms. Now, if you take something like biosciences, it's also treated in a very materialistic way. You are treated in a very materialistic way in the sense that everything has to do with your DNA, which is just a kind of sequence of 4 letters that repeat themselves and give you your supposed characteristics. And most of the things you eat today, that sequence has been modified in some way, genetically modified foods you eat. But there's also another way you can think about life, and that is, this was from Nature, which is a quite famous journal. You can also think of life to be a very dynamical phenomena. So at this moment in your body, every cell is actually full of little molecular machines that are moving back and forward. And this is something that I became very interested in nanoscience. And the way we started this work was actually to look at yeast. Yeast is, you find it in beer, you find it in bread. And we started to study the actual motion of yeast cells. And this is the paper Maurice is talking about. It was published in Science a few years ago. And we use a thing called an atomic force microscope, which is actually a type of finger, but it's on the nanoscale. So a yeast cell is about something like a 20th the diameter of your hair. And if we use a very sharp tip, we can record the motion of the yeast cell, somewhat like you would record in the old days, if you remember, gramophone records, okay? You can pick up the motion of the music and the grooves. So we don't need to move this thing, but we just follow the motion of the yeast cell. And what we discovered was something kind of very strange. That is, on the scale of a nanometer, and I mean, it would be like 10 atomic diameters, very, very, very small, we found a distinct oscillation. And this is a plot of that oscillation recorded on, on the nanoscale. And the time scale here is such that it puts that motion of the yeast cell into the audible range. Now, it's actually an inaudible phenomena normally because the motion's so small. But what we did was we did not change the tone, but we just pumped up the volume. And this is 22 degrees centigrade, room temperature. This is how yeast sounds, so maybe a bit loud, okay. I like it loud. That's good. Okay. And so yeast cells, something collectively is moving inside them that causes this motion, this type of motion. Now, when we change the temperature just by a little bit to make it warmer, you can see the pitch increases. And if you heat it up even more, it's more active. Now you hear a much higher pitch. So the pitch depends on the temperature, and we actually used that information to work out what type of machinery was going on inside that cell that caused the motion. And our conclusion was that it's these small molecular motors called myosin that are moving, but individually, one is not sufficient to cause a massive effect. And the type of effect we saw actually relies on the fact that all of these molecular motors somehow are working together. And so there is a kind of, it's like an orchestra. Somehow inside that yeast cell, they all work together. So this piece here, we actually generated into a kind of installation, and the installation was originally for fun, and we had the Integratron, which is a dome. It's a dome out in the Mojave Desert. And we had some blue lights, and we had an area where people could think about change, think about changing their own lives. And they would sit in the center and be surrounded by other people. And it was meant as a light-hearted piece. But it turned out the piece should have ran, I think, from 7 o'clock to 9:30. It actually went on until 2 o'clock in the morning because the people just meditated, and we couldn't get them off. And they took it so seriously. Then we ran it a second time, also in the Integratron. We were sold out. People came from everywhere. Even one came from New Zealand. And they were queuing up outside. And one guy was really angry. He said, I should have, it should have started now, and so on. And Victoria said to him, well, you can have your money back. And he goes, bleh, bleh. He sat down on that piece and meditated and listened to those sounds. And he was transformed. He was so happy. It was the best moment in his life. So what's really strange is, and I still don't understand it, what is going on with the sound and the meditation and this type of process. So what we do at the moment is try to study human cells. And that has been a piece of ongoing work where we worked with the UCLA Medical School, mainly studying how soft cells are, because it's very hard to pick up motion, but there is motion, to differentiate cancerous cells from non-cancerous cells. And I believe that in the scientific world we live in at the moment, there's always this desire to think in a very reductionist way. But when we work in nanoscience, it's actually something that inspires one to think a bit in a broader way. So the concept of just pure materialism, DNA, pure materialism, thinking of atoms of gold, is perhaps something that people could do with a kind of alternative view to the world, an alternative view. And if you look at atomic atoms, even from the point of view of fundamental particle physics, what explains it is string theory. And string theory is vibrations. There are vibrating strings made out. There is no matter at the very, the very highest levels of physical theory. And I think as we look perhaps at people and human beings and illnesses, maybe in the end we'll find that the traditional Chinese medicine people are actually maybe more in tune with the world than we are. We're a materialistic world. So with that, I'd like to thank you all.
A scientist said, "You're killing more cancer cells than as if you had used radiation." That same scientist went on, "If you had spent millions of dollars developing a new drug that killed this many cancer cells, it would be a home run." This was an astonishing thing to hear, especially for a music professor who had just completed his first experiments in a cancer lab. But we didn't use any radiation. We didn't use any drugs. So what did we do? I have here two identical tuning forks, both tuned to the note A, the note an orchestra tunes to. These forks are both made to vibrate 440 times per second. We say their frequency is 440 hertz. If I tap this fork, putting little pulses of energy into it, the second fork will also vibrate in sympathy. And if I silence this fork, We just may hear the other singing its tone. We say that I'm inducing a sympathetic resonant vibration in the second fork. It only works because both forks are tuned to the exact same frequency. Now, many of us have seen this very charming young man on the internet who shatters crystal glasses with his powerful voice. But if you watch him carefully, you'll see that first he taps the glass with his finger and listens. The glass sings its natural resonant pitch. Then he takes a deep breath and sings a loud, long note. He induces a resonant vibration in the crystal glass. The vibration grows larger and larger and larger until the glass is shattered. On the other end of the scale, we have a giant bridge made out of concrete and steel, a suspension bridge, the Tacoma Narrows bridge. Cars and trucks and buses are going over it every day. And unfortunately, where they built this bridge, there was a steady wind blowing across it. And one day this wind induces a small vibration in the bridge, hardly noticeable. But the frequency of the vibration matches the resonant frequency of some part of the bridge. And the vibration gets larger and larger and larger until the bridge collapses into the river below. A destructive resonant frequency. So on one end of the scale, we have a giant concrete and steel bridge destroyed by resonance. And on the other, we have a small crystal glass shattered. So maybe we could shatter something even smaller, something really small, something you would need a microscope to see. Maybe we could shatter a living microorganism. But to do that, you'd need some sort of theory to serve as a basis. And we find that basis in a wonderful book called The Rainbow and the Worm, The Physics of Organisms, by a scientist, Mei-Wan Ho. And the hunt begins through a microscope for a frequency which will shatter a living microorganism. Now, we have a method of controlling Dr. Baer's device by an input control frequency. So if I put in, say, 100 hertz, out will come 100 pulses per second. If I put in 200 hertz, we'll get 200 pulses. So now we're searching for the magic frequency. And we start with 100 hertz, and we look through the microscope to see if anything's happening. We watch for 5 minutes. Nothing happens. So we try 101 hertz. We look through the scope for 5 minutes, and nothing happens. So we try 102, 103, and so on. Over the course of 15 months, we try hundreds and hundreds of frequencies, if not thousands, until we find the magic combination. The answer is you have to have 2 input frequencies, one low, one high, and the higher frequency must be 11 times the lower. It's what we musicians would call the 11th harmonic. And when we add the 11th harmonic, we begin to shatter microorganisms like a crystal glass. These are the first videos taken. We showed these videos to our friends in the biology department. They said they hadn't seen anything quite like it. Seems to be a new phenomenon. These organisms are being shattered by our electronic signals. This is a harmless organism, almost friendly, a little blepharisma. And normally they're very fast swimmers, but when you approach a frequency to which they are vulnerable, they begin to slow down, then they stop, and then they begin to disintegrate within about 3 minutes. So now we know we can destroy a microorganism, And the question comes up, but can you target a specific organism with a specific frequency? So in this next video, you'll see a large organism in the center, a paramecium, undergoing disintegration, and swimming all around it, a tiny different organism, which is unharmed. If we're lucky, we'll also hear the audio as I narrate the experiment live in a noisy lab. Perhaps you can see the sort of fireworks effect happening in the growing blister to the right of the organism. And here comes a little neighbor, wondering what's going on. Who's testing. And you can see blisters forming now on the lower left quadrant and upper left quadrant. The shape is now changing. And a major explosion out the top. So now we have some evidence that we can target specific microorganisms with specific frequencies. And we make several more videos, and we film the destruction of hundreds of microorganisms. And about this time, we meet a cancer researcher, and we show them these videos. And this results in an invitation to spend 4 months in a cancer research lab trying to shatter cancer cells. This is our setup in the lab. You can see the microscope with cancer cells on it. Here's the plasma tube, and here's my little frequency control box. So first we attack pancreatic cancer. Take a good look at this slide, because the next one will look quite different. After we treat these cells, they change their shape and size, and they begin to grow long, rope-like structures out the sides. They look something like antennas. I call them bioantennas, for biological antennas. It's as if the cancer cells are trying to tune in to our signal. It also turns out this is the beginning of a process of destruction for cancer cells. We now know that cancer is vulnerable between the frequencies of 100,000 hertz and 300,000 hertz. So now we attack leukemia cells. Leukemia cell number 1 tries to grow a copy of itself, but the new cell is shattered into dozens of fragments and scattered across the slide. Leukemia cell number 2 then hyperinflates and also dies. Leukemia cell number 3 then tries to make another cancer cell. The new cell is shattered and the original cell dies. But killing a handful of leukemia cells is not enough for a patient. What kind of numbers can we do? In repeated controlled laboratory experiments, independently assayed by the 2 top experts, we killed an average of 25% to 42% of the leukemia cells, as high as 60%. They also determined that we slowed the growth rate of the cancer by as much as 65%, so a double effect. Now we attack ovarian cancer cells. This is a more distant shot. Here you see brackets coming up around the cells, showing groups of ovarian cancer cells which are being destroyed. You can see by the end of the video that a great many ovarian cancer cells were destroyed. Now we attack pancreatic cancer once more. In the center of the screen is a clump of pancreatic cancer cells, like a microtumor under the microscope. We turn on our electronic signals, and the tumor shrinks and is broken up. The cells are disconnecting, disaggregating, the opposite of forming a tumor. And some of the cells are destroyed. In our most recent work, we attacked the deadly organism MRSA. MRSA is particularly dangerous because it's resistant to many common antibiotics. Thousands of people die every year from MRSA. They have drugs for it, but they have very toxic side effects. We found that our electronic signals could actually eliminate antibiotic resistance in MRSA. Then by adding a very small amount of a common antibiotic, we were able to kill MRSA and slow its growth rate. Since I was a 17-year-old high school student with twin interests in both music and science, I never imagined the two would come together in a cancer research lab. I now believe that the future cancer treatment rooms for children will be a very different place. It will be a pleasant place where children gather and make new friends. They probably won't even know they're sick. They'll draw pictures, color in their books, play with their toys, all the while unaware that above them are beautiful blue, pinkish plasma lights emanating healing, pulsing electric fields, shattering their cancer painlessly and non-toxically, one cell at a time. Thank you.
This is a short instruction video on how this type of vocal sympathetic resonance system works, or the VSR system for short. Let's start off by using the piano keyboard to begin to explain this. Normally pianos have 88 keys. Here we're only going to show off a few keys to keep it simple and compact. Each of these 88 keys have their own separate note or sound frequencies, which is measured in hertz. As you see here, I have the keys labeled, and if I play one, their corresponding note value shows up here, and their frequency value shows right here. Once again, A4, A4, and as you can see, this is the frequency 441 or 440 hertz approximately for their frequency, or for its frequency. Each of these individual notes or sound frequencies can make up chords. An example of a chord would be a C major chord, which is comprised of a C4, E4, and G4. And when you combine all these, you get a C major chord, and it sounds like this. Now the C4 chord is 261.6 hertz or so, approximately, as you can see here by the cursor. And if we go to E4, it's around 329, 330. And a G4 is about 393, 392. And once again, if you combine all these notes or sound frequencies, this is what it sounds like. This now brings us to explaining to what exactly is a harmonic. A harmonic is basically, in this graphic here, is if we start off with 440 hertz, all you have to do is basically double that number. So if we start with 440, we will get to the second harmonic by doubling it, which would make that 880. To triple it, 1320, and the fourth harmonic, 1760. Whereas a piano has 88 keys, a person's vocal sympathetic resonant keys, or individual notes, will vary depending on the vocal snapshot or audio wave file that is sent in to us. The Vocal Sympathetic Resonance System, or VSR, we use calculates personal resonant notes, or PR-N. An example would be in the note A4. Here on a regular Yamaha grand piano, it's approximately 440 Hertz. Now A4 would represent a different PR-N, or personal resonant note, based on your vocal snapshot. So if we go to an example of a personal resonant note snapshot preset and do the same note, notice how we get something completely different. Once again, a Yamaha grand piano, A4, 440 Hertz approximately. Then your personal resonant note calculated from the file you sent in to us and how that actually sounds. And moving on to personal resonant chords, or PR-C, would be made of personal resonant notes, or PR-N. Like a C major chord is made up of 3 notes: C4, E4, and G4. Your personal resonant notes also make up personal resonant chords. So, to test that, we do C4 for your personal resonant note, E4, and G4. Now to make a personal resonant chord as a C major chord, this is what that sounds like. And next we have a personal resonant harmonic, or PR-H. Would be twice the harmonic of the PR-N, or personal resonant note. Just like A3 is approximately 220 Hertz, the harmonic of A3 would be A4, which should be approximately 440 Hertz. So the same is also true if we use your personal resonant notes to get a personal resonant harmonic. So this is what it would sound using the A3. And a harmonic of that would be the A4. And please note that there's an entire scale. Creation of the Vocal Sympathetic Resonance file, or VSR for short. How do we create your file using this type of vocal sympathetic resonance system, or VSR? 1. We take the audio file you send to us and we run various calculations on the file using fast Fourier transforms, or FFT, to calculate the personal resonant notes, or PR-N, found in the file. 2. We then create the personal resonant chords, or PR-C, along with the personal resonant harmonics, PR-H. And finally, we then assemble these files and send it back to you. Okay, in this video we're going to show you or give an example of what the type of file you would send to us and the type of file we would send back to you. So let's go ahead and bring the file that you would send to us, what that would actually sound or sound like. It could be a mantra, affirmation, or a combination of mantra and affirmation. The things we require is that the file be at least 44/100 hertz, the sampling size that is. It could be mono or stereo, or 16-bit or 32-bit float. This file is just a mantra. Let's go ahead and play that. Om Ame Di Li Gong Zhong Hom Ame Di Li Gong Zhong Hom. Okay, and that's the type of file you would send to us, which would be approximately between 35 and 40 seconds in length. And we will start the next video dealing with the file that we would send back to you and what that actually would sound like and what that would actually look like. In this video, we're going to demonstrate the type of file we would send back to you and what it actually sounds like. Okay, the file we send back to you is in stereo, and the sample rate is 44.1 kHz, or 44/100 hertz. And keep in mind the resonance, or the resonances we send back to you in this file, more than likely won't be the same resonances you hear in this particular video, due to the fact that each person has their own resonant file or own resonant frequencies. So what you hear in this video more than likely won't be what you hear in the file we actually send back to you, because each specific file is calculated to the file you send to us. So each time it's geared to that particular person. Let's go ahead and play that. And normally the length of the file we send back to you is around 20 minutes, but that can be adjusted. Okay, and that's the type of file or the way it would sound generally when we send it back to you. In conclusion, my goal is to not only stimulate the system using sympathetic resonances, but also to open up the system. By using resonances to gently rock the system back and forth, this should allow the opening up or freeing of movement in the system. Much like that of freeing a car stuck in the mud, this should allow the natural flow of the system to once again take place. The conductor. You can play 88 keys on a piano, but there are an infinite amount of unplayed and unseen keys or notes between these 88 keys. Remember how to play the unplayed, and remember how to see the unseen, for a grand symphony orchestra is patiently awaiting their conductor. Now, excuse me while I go compose my magnum opus, using the unseen and unplayed keys.